about spin. And we established that there was something causing this fine structure in the emission spectrum. It's always useful to take a moment of pause and think, okay, so where does the idea of spin even come from? And they noticed this, this structure. That's one experiment. It's not the only experiment. There's another experiment where they had some silver atoms flying through a magnetic field, and it indicated they had a quantized magnetic moment. And so there's other things as well, but we have apparently a moment for the we simply weigh the equation. So we have to forget about trying to use the Schrodinger equation because it can't exist. But we can still use our eigenvalue, eigenvector relationships, our matrix methods. So that's what we're going to do when we deal with spins. So it's kind of interesting when you look at the complete wave function for an electron. You have a function that's a function of x and t, and then times what can only be given as a matrix, not as a function.
Wait, so why can't you have a wave function?
Because this is something intrinsic. It just has this property. And, it's like you don't have a wave function for mass either. So it turns out that, and we've already seen this slide probably twice. It turns out that when we were looking at angular momenta, if we looked carefully, because we didn't look at this equation carefully, it allowed for either integer or half integer angular momenta. It doesn't allow for anything else. You can't have, 3/4 integer angular momenta, but you can have half integer or integer variations. And that's where I talked about the difference in the fermions. Fermions are any particles that have 1/2 integer spin, and bosons are things with integer spin. And when I say spin, what does that mean? Okay, but it's referring to the intrinsic angular momentum or intrinsic magnetic moment. And so I said angular momentum here. We're going to use all the rules we've learned for angular momentum for spin. And if you really care, if you do particle physics, like you talk about protons and neutrons and that kind of thing, you find that there is another behavior they call isospin. It behaves like spin, but it's something different that once again is going to follow the same rules. So using the same operators with the same eigenvalues. So S squared operator is the operator giving me the total spin angular momentum squared. And that should be equal to h bar squared times s times parentheses s plus 1. And it's going to have the same state, so we put s m sub s for the state. Now for an electron, what is s always going to be? 1/2. So it seems silly to put it in there, but we are right now, just to make sure that we don't forget that we have both the spin and the orientation of the spin. So if you put that in, you have s squared is always going to have this value, 3/4 h bar squared. So the total angular momentum for an electron is always square root of 3 times h bar over 2. And then if you want it in the z direction, using exactly, once again, the same operators we used before, we have plus or minus h bar over 2. So just like with angular momentum, you can draw a circle with radius of root 3 over 2 h bar, and that's the total spin angular momentum. And then you can indicate the allowed values, which are h bar over 2 and minus h bar over 2. And then that tells you the orientation of the magnetic moment of the electron must either be like that or like that, where the z-axis is up and it's the xy plane that we're going across horizontally. So what this is saying is you can't have the angular momentum completely in your z-axis. It's going to be partially the z-axis, partially the xy plane. And you don't know where it is in the xy plane because you can't know the x component and y component and z component simultaneously. But what you know is it's doing something circling about that axis. So we're going to build up these operators, these operators. So we know that s squared on state 1 is equal to h bar squared times 1/2 times 1/2 plus 1, state 1, right? That's what we know because we have the eigenvalue and we have the, and the eigenvector is state 1. It's just what we're calling it here. And so that means that, well, what else do we know? We know s squared on state 2 is equal to h bar squared. So that means if we're going to make a matrix, it's actually really simple. You have 1, 0, 0, 1 times 3/4 h bar squared must be the matrix. So we have that so that you can then see with 1 equal and 2. So we're going to talk about these. These we call spinors, by the way. The spinors are the two states. It doesn't matter which state I'm in, I'm going to end up with the same spin. I actually could have had any set there and it would have worked. Now for the SZ, it's a little more complicated. SZ so you have like that. SZ operating on state 1 gives me h bar over 2 times state 1. And SC operating on state 2 gives me minus h bar, forgot the bar, over 2 state 2. Now I didn't write this the first time, but I'll write this time. If I want to write this all kinds of pedantically, this means I have SZ sub 1 time, well, that's essentially what I have from the first equation. Right, SZ being this A, B, C, D. This is a C, it looks like an E. And then EF is my state 1. And so we simplified things with using state 1 as 1, 0. So just put 1, 0 there. And then you have, okay, so A times 1 plus B times 0 is equal to h bar over 2. So A had to be h bar over 2. And C times 1 plus D times 0 equals 0. Therefore, we must have C equal to 0. And so we have A and C determined by this first one. Backing up just a step, how did I know that 1, 0 was going to work? I didn't really, did I? It is, we know that our states 1 and 2 have to be orthogonal to each other. And that is a pair of orthogonal vectors. And so I kind of arbitrarily chose a pair of orthogonal vectors, and I might have ended up with a non-diagonalized matrix by randomly choosing that way. But that was just a choice to make 2 orthogonal vectors and see how it works out. And so I found that A is h bar over 2 and C is 0. Now, if I were to go and repeat this, except for change that from 1, 0 to 0, 1, because I'm out of space, I'm not sure why sometimes it doesn't accept it when I change the color. If I do it with the second one, with state 2, I would have A times 0 plus B times 1 equals 0. So that gives me B must be 0. And I'd have C, which I already know is 0, C times 0 plus D times 1 equals h bar. Oh, it's minus for this one, so minus h bar over 2. So that tells me D is equal to minus h bar over 2. And that's how I get my matrix.
Okay, so when you're going from one state to the subsequent state, you always switch the h bar over 2?
Well, the sign was different because we have spin up and spin down is the eigenvalues were plus or minus h bar over 2. And so that's why one had a plus and one had a minus.
Yeah, so if you went on to state 3, then it would be plus h bar over 2 again, or how are you determining that?
I'm determining that because that's all that's available. There is no state 3 possible. It's a 2-state system. Right, and it comes from the rules on the L sub z's that we learned. That the M sub L had to be between plus L and minus L. And so M sub S has to be between plus S and minus S. S being a half, it can only be plus or minus a half. Those are the only 2 options. So there is no projection into a third or extrapolation to a third. Okay, so that's how these 2 matrices come about. And you can see this is the matrix we just determined, the second one, SZ. And of course, we've already identified these as our eigenstates. This is putting it in S, comma, M sub S form. Notice it's a plus on the top and a minus for the bottom. Or sometimes we'll use an up arrow for spin up, a down arrow for spin down, or we'll use a chi plus and a chi minus. So all of these on top are equivalent to each other. They're all equivalent representations. All of these on bottom are, once again, equivalent to each other. So when we call them the spinners, they're the spin states. Won't get confused if I use an up arrow versus a chi plus versus a matrix versus S comma M sub S. I saw this typo after this. This is the same slides that we used last class. Well, Friday, Wednesday. Would you believe? We don't have class on Friday. Using the relationship, remember for the homework problem that we did yesterday, I put A sub plus and A sub minus, so I didn't have to write all this stuff out the first time. And so this here is that same A sub plus or minus, and the only difference in the two is this plus or minus 1 here. So S plus or minus acting on a spinner should give me, if it's a plus, it's going to raise the state. If it's a minus, it's going to lower the state. And this is the eigenvalue that goes, well, it's not really an eigenvalue, is it? Why is it not really an eigenvalue? What's the eigenvalue eigenstate relationship? Operator acting like gives you eigenvalue times the original eigenstate. This isn't returning the same state. So this isn't an eigensystem. So I shouldn't use the word eigen for this here. But it allows us to build a matrix for Sx and Sy. So I want to do that. Chad came in while I was practicing before my last class. So just like in the homework problem, S plus is equal to Sx plus I Sy. S minus equals Sx minus I Sy. So if I combine those, S plus plus S minus equals 2Sx. So Sx is equal to S plus S minus all over 2. That should look very familiar. And so will the rest of this. So now if I have Sx acting on, well, I will put it like this, 1, 0, that would be 1/2 S plus acting on 1, 0 plus 1/2 S minus acting on 1, 0. What is S plus acting on 1, 0? If the spin is 1/2 and I raise it, what do I get? If I lowered it, I would get 0, 1. This is already M sub S equals plus 1/2.
Okay. I was thinking that it's higher energy to be in the negative 1/2 state.
We're not talking specifically about energy here. We're talking about the spin orientation. It will have energy implications, but it depends on the other spin orientations, what its energy implication is. But if we're already in the upper, right, the higher spin state, and we try to raise it, what do we get? 0. This term is just going to give us 0. What do we get if we lower it? Not 0 for lowering it, because we're in the upper state. It'll go to the, what was that?
0, 1.
Yes, 0, 1. So we're going to get 0, 1, and then we have to put in what this A minus value is. So that's going to be, notice S times S plus 1 is always going to be 3/4, 1/2 times 3/2. And then minus, and if it's the negative, then it's 1/2 minus 1/2, or minus 1, so it becomes minus 1/2. Ugh, I messed that up. If it's negative, you have minus, parenthesis, minus 1/2. I am so not doing math right today. The M is 1/2. So it's minus, parenthesis, 1/2 times 1/2 minus 1. 1/2 times 1/2 minus 1 is, of course, 1/2 times minus 1/2, or 1/4 minus 1/4. Minus a minus means plus 1/4. So that's going to be 3/4 plus 1/4, or 1. Yay! So that's just going to be H bar times 1. I guess I gave myself way more space than I needed. So that's what we get by applying the lowering operator to the upper state. And so there's our SX value. SX acting on 1, 0 gives us 1/2 H bar 0, 1. And then if we do SX acting on 0, 1, we get what? My finger must have been hitting something funny. Go away. There we go. I'll hide that. So what are we going to get when we have S plus acting on 0, 1? It's going to go from MS is equal to minus 1/2 to MS is equal to plus 1/2. And then we have to do this. Now we're going to have the raising. So with the raising, notice I'm keeping this minus sign with them. So I have minus 1/2, minus 1/2 plus 1. Well, minus 1/2 plus 1 is plus 1/2. Minus 1/2 times plus 1/2 is 1/4. Minus 1/4 with the minus outside. That's again plus 1/4. So again, I have square root of 3/4 plus 1/4, square root of 1, which is just 1. So I just have H bar just like I did before. And what do I get when I put the lowering operator on M sub S is minus 1/2? 0 again. When you put the lowering operator on the low, then you get 0. So we have now two relationships. I can again put A, B, C, D acting on 1, 0 is equal to 1/2 H bar 0, 1. So A times 1 plus B times 0 equals 0. Therefore, A equals 0. C times 1 plus D times 0 equals 1/2 H bar. Therefore, C equals 1/2 H bar. Now going to the blue one, I have, again, A, C, B. Oh, crud. I did the right thing. This here was the blue one. Blue and red, red and blue. I'll change that. That's very poor color coordination. Okay, there, fix that. So now to go into the red one, A, B, C, D, 0, 1 equals H bar 1, 0. And we have A times 0 plus B times 1 equals 1/2 H bar. Therefore, B equals 1/2 H bar. And C times 1 plus D times, or C times 0 plus D times 1 equals 0. Therefore, D equals 0. And so what we have now is 1/2 H bar everywhere. And then it was B and C are going to have 1. So we're going to have And then we can do the equivalent work with the minus. And just like what you're doing in the homework, with the minus, you're going to have s plus minus s minus is equal to 2i sy. And so it's going to have a minus sign and an I difference. So here, well, that's not exactly. I had and if we had done the sy, we would have had h bar over 2, 0 minus I 0, the minus sign and the I were the differences. And then we've already seen that sz was equal to h bar over 2, 1, 0, 0, minus 1. And so this gives us our Pauli spin matrices. You take away the h bar over 2, the matrices that are left are the Pauli spin matrices. So Sx is equal to h bar over 2 sigma x, Sy equals h bar over 2 sigma y, and Sz equals h bar over 2 sigma z. So these matrices are things to make our lives easier. And we can check some of our basic relationships. We've learned, for instance, that s squared should equal sx squared plus sy squared plus sz squared. So using these Pauli spin matrices, this is going to be h bar over 2 quantity squared times sigma x squared plus sigma y squared plus sigma z squared. And let's just calculate what the sigma x squared is and sigma y squared and so on. So sigma x squared is equal to how do we multiply a matrix? Okay, so that's 0 times 0 plus 1 times 1. Then what? Okay, so that's going to be 0 times 1 plus 1 times 0. Going down to the second row. Second row with first column is 1, 0, 0, 1. And then the final one, 1, 1, plus 0, 0. So you multiply those through, you have top position is 1, next position is 0, 0, and 1. Sigma y squared is so if I multiply those through, I'm going to have minus I squared for the first term, and then 0 for the next one. Then the third one is going to be 0 again, and the final one is going to be I times minus I, so minus I squared. But what is minus I squared? What? And the final one and so sigma x squared is equal to sigma y squared is equal to sigma z squared. They're all unit matrices. And so if we add those together, we're going to have 3 times the unit matrix. And that's indeed what we had already established that s squared was. Let's try something else that's fun. Commutators. We've already looked at commutators. what is the commutator between, let's say, Sx and Sy? Does it look right? So if we do that multiplication, we have that when we put in the matrices. Oh, that's plus I. And
Why did you have plus sign first?
okay, so are you talking about this here? Okay, so that's this times this plus this times this.
Oh,
I put the minus sign
Yeah,
first by
I was
accident
too.
too. So when we do that, notice I have I minus a negative I. First, I was really worried because it looked like it was going to disappear. So that would be 2I, 0, 0, minus 2I. What do we have then? Okay, so that there I'm factoring out one of the h bar over 2, so I have another h bar over 2 remaining. And then there is this 2 here remaining and the I remaining. So what is this first thing that I wrote out?
let's see.
So it's SZIH bar. So I checked my commutator relation there using the matrix multiplication. Obviously, you could have done that too, but just showing the kind of thing we can do with the Pauli matrices. Now we're going to go to a problem. Suppose a lone electron is held at rest in a strong magnetic field of magnitude B0 in the arbitrarily defined z direction. What happens? So we need to determine what its energy is going to be, first of all. And so I gave you the Hamiltonian is minus mu dot B, where mu is the magnetic moment, which is, do you remember what this gamma stands for? Yeah, the gyromagnetic ratio, S dot B. So S dot B, what direction is my B magnetic field? Arbitrarily defined Z direction. So that means S dot B, since B is in the Z direction, it's going to be B times SZ, right? In general, but since that was 0 and that was 0, that's why it collapses to something simple. And so my Hamiltonian now, I have a Hamiltonian, but it's just matrix. It's not a wave function. And so I have the minus sign, the B, SZ, B here, SC is H bar over 2, 1, 0, 0, minus 1. And now we immediately know, okay, so the eigenstates of the spinors, or excuse me, the eigenstates of the Pauli matrices are the spinors. So we have two states, one corresponding to spin up, one corresponding to spin down. And the eigenvalues, when it's diagonalized, you can read the eigenvalues, right? When it's diagonalized, the eigenvalues are just the diagonal elements. And so this is going to have eigenstates of plus gamma B0 H bar over 2 and minus gamma B0 H bar over 2. So we're able to quickly, very quickly here, determine what the energy states are going to be. And we're going to have two energy states by having this electron in the magnetic field. Now, what's the electron going to naturally do? This is something I think you said earlier.
Orient itself.
Okay, it's going to orient its moment so that it goes to the lower energy state, right? So it's naturally going to go to the lower energy state, but it can go to the upper energy state. And we see this, and it's very important in astronomy. Hydrogen, the one that we can do, we can perfectly solve hydrogen, we believe. It has the energy difference between these. If it's not in an external magnetic field, if it's only dealing with the magnetic moment of the nucleus, it has a very small energy difference. And because of collisions, you can have it absorb energy and get flipped and then fall back down and give off radiation that is in the radio range. And so we tune our telescopes to look for this radiation that's given by the electron flipping from being aligned with the magnetic moment of the nucleus to, well, against it to with it. And actually, a second. I've got to get my fingers straight. But flip going from the higher state to the lower energy state. And we can see that, and thus we can map out where clouds of hydrogen gas is. And so it allows us to map out something that we could otherwise never see. I know I'm early, but I simply, this here is a mess, and I don't want to do that. What I want to do next is to simply go to, I guess I should go through this because it has an important thing. You guys do NMR, right? This is the basis for NMR. When it says chi plus, what does that mean? It's not. I can totally see why you said that, but it's not. That's that's the positive spinner. Depending on where you look in the book, it uses different symbols. Depending on what software I'm using actually for math, I'll use different symbols. And so this is some constant times the upstate with the time variation for the upstate, and then a different constant downstate and your time variation for the downstate. So this is some arbitrary A and B, your superposition between upstate and downstate. It turns out that E minus and E plus are the same magnitude, right? We just found that right here. So you can put that magnitude in here, whoops, over 2, and the H bar canceled out. There was an H bar here that canceled with the H bar here. And so we now have something that has the plus state, that's 1, 0, the minus state, 0, 1. And so if we put these together, I'm going to have A e to the I gamma B0 T over 2 in the top, B e to the minus I gamma B0 T over 2 in the bottom. And so this here represents the state of an electron that is, some arbitrary combination of being in the up state and the down state when it's put in a magnetic field. So far there's nothing special here. There's just, this is how we can write the state. And, if you go through time, the top one's going to sometimes be 0, the bottom one's going to, or the real part will sometimes be 0, right? This is real imaginaries. So if we calculate the expectation value for spin in this state, the expectation value is always for the state. And so if I do expectation value for the spin in the x direction, well, I just multiply this through. So multiplying it through the vector in the matrix, the first thing I did is multiplied these two. So I multiplied those two to get, actually, nope, take that back. I multiplied these two, because the last one stayed the same. Multiplied those two, so what it did is we had this one in the first term. This one, I changed the erasable. This one here in the first term because it's 0, 1. And then this here in the second term because it was 1, 0. So basically flip the position of these two. And then multiply these, so I have this times this, gives me this. Notice I had the AB out front. And then this times this gives me this, AB out front. And in this case, e to the I theta plus e to the minus I theta is, well, I should just write that out. In case you're not familiar with them, that's a 2i. Those are definitions for sine and cosine. And so this right here is simply 2 cosine theta, where theta is gamma B0T. So the AB was factored out front. The h bar over 2, when you multiply by 2, it just gives you h bar and cosine. So what does this tell me about the expectation value for the spin in the x direction? It tells me that the expectation value is going to be varying. It's going to go back and forth, back and forth, back and forth. And if I do in the y direction, the difference in the x and the y is minus I and plus I. So it's going to change the sign when I do the first multiplication. You see that sign change there. And then we have an I that comes out front. And so we have a subtraction, which gives us this. If you combine this 2i and that, that's sine. And so you have minus AB h bar sine. So once again, it's going back and forth, but out of phase. So they're going, which, if you look at it like this, turns out to be going in a circle. So what this then says is that we're going to have the magnetic, oh, come on. we're going to have the spins. Wow, I really got off. The spins will precess an XY plane with omega is equal to gamma B0 H bar, if I remember right. Gamma B, no, just gamma B0. So we have the frequency for it to be going around the circle is determined by the strength of the magnetic field. The stronger the magnetic field, the higher the frequency.
We didn't calculate the SC though.
Right, we just did X and Y.
We did do X. Okay. Yeah.
Yeah, we did X and Y. Okay. And so, yeah, you asked about the Z. Well, what is our expectation value for Z? A e to the minus I'll put the H bar over 2 out here. Minus blah BE to the plus blah. Okay, so round space. So if we do that, we have multiplying first the first vector and the matrix. I have where I use that squiggle for the stuff that's the same in all the exponents. So I have that. Well, what's that, you ask? First of all, we have a squared minus b squared, so it's not going to simply be a sine or cosine because we have different percentages of each one. And so it's more complicated. And I'm not ready to do that. Yes, I am. Okay, so here, wait a minute. Oh, I made one fundamental mistake. When we do this here, it's of course the complex conjugate when you make the bra. And so I put the wrong signs here. And so these E terms are just going to give you 1 because you have the minus with the plus. And so it's a constant, which is better. A squared minus b squared. So we have h bar over 2 a squared minus b squared is the expectation value for the z direction. That's a constant, which is much better because that's what we expect. We expect that it's not going to be changing. It's a stationary state.
Why did you just get rid of that?
Because e to the minus I gamma b0 t over 2 times e to the plus I gamma b0 t over 2.
Right, yeah, but I mean.
That's e to the 0, and e to the 0 is 1.
Yeah, at the ends of the 3/4 h bar squared. No, on the next page.
Here, okay.
Yeah, on the last line,
Oh.
that 3/4 h bar squared, b squared plus b squared, and then you just reduce it to 3/4 h bar squared.
Okay, so this here is doing s squared, right?
Oh,
This
okay.
here was the answer for the sz.
Okay.
And then doing the s squared, I have a 0 where there should have been a 1. There's no justifiable reason for having a 0 there other than error. And so if we do this, the 1, 0 isn't going to change anything. So fundamentally, you just drop that out. You have the same things here. This times this is going to be, again, that's a plus, that's a minus. And this times this plus and minus, both of those just give you 1. And I have a squared plus b squared because I didn't have the minus sign here like I'd had there. And so that's why this is a squared plus b squared. And by definition, a squared plus b squared has to be 1 because it was a superposition state. So you had a squared is the probability that you're in the up state, and b squared is probability of the down state. The sum of those has to be 1.
Okay.
Okay, we're done.